So in class number 1, it's showing a ferromagnetic core. The depth of the core is G, and the other dimensions of the core are as shown in figure. So these are basically, this is a magnetic core, A, B, C, and so on. And G is the depth of the core. We're assuming that there is a relative permeability associated with this core, which is constant and equal to mu r. We want to find out the reluctances of the upper, lower, left, and right sides of the core in a certain unit, kiloamp turns over Weber, and find the value of the current that produces a certain value of flux, phi, in Weber. And we want to find the flux density at the upper, lower, and right sides of the core. Okay? So before going into this, I've also given you the inputs of the problem here in the live script, which G is going to be 5 centimeters, A is going to be 10 centimeters, B 20 centimeters, C 5 centimeters, D, E, and F, they're all given also as 15 centimeters. The phi, or the flux that we're going to expect, is 0.005 Weber. Mu r, or the relative permeability, is 800. And the number of turns is 500. And mu 0 is also equal to 5 pi times 10 powered by minus 7 Henry per meter. So these are the inputs of the problem. So typically, I assign all the problems in this form, give you the problem statement, and give you the inputs here. And your job will be to come up with a procedure and showing us the outputs in the required units. But before going into this problem, it's a good idea to basically have all the physical quantities that we talked about and write up the names, their type, and their SI unit. So this document I'm going to upload also in Canvas for your further reference. Let's go over a review of that. So we talked about H and B, which were both vector quantities. H was magnetic field intensity, and B was called magnetic flux density. The units, the SI unit for H is ampere per meter, or ampere turn per meter. Ampere turn is related basically to the cases that you have a number of turns that are producing that magnetic field. So in that case, in order to show the effect of turns, we use the ampere turn instead of ampere. B was the magnetic flux density, which is also a vector. Its unit is Tesla, or Weber over meters squared. Phi is magnetic flux, scalar in Weber. Mu is permeability of the magnetic material, and scalar in Henry per meter. I is current, scalar amps. Reluctance is a scalar ampere turn over Weber, or 1 over Henry, or Henry minus 1. P permeance scalar Weber over ampere turn, or Henry. Same thing for inductance, is also a scalar and Weber over ampere turn, or Henry. And flux linkage is in Weber turn. So that turn is really associated with the case that for flux linkage, the difference between flux linkage and phi would be by n. So lambda would be n times phi, where n is showing the number of turns in the winding, right? So I'll go ahead and upload this. We may always forget the units. So the more you work with the problems, the better they will stay in your mind. So let's go back to the problem. So if I want to make an analogy between this magnetic circuit and a certain electric circuit, we want to draw an equivalent circuit diagram for your magnetic circuit in here. You would have a source here. Your source has an F, or MMF, magnetomotive force. So this magnetomotive force could be direct, could be alternative. In this case, because our current is, or your phi is going to be constant, it means that the current is going to be constant. So therefore, it would be, in this case, it would be a direct circuit. So I put just a plus minus, or we can show it this way. And then we have basically a certain reluctance in each of these paths. So this path could have its own reluctance of what I called reluctance of the left-hand side. So RLF. Then you have a reluctance here on the upper side, a reluctance on the lower side, and a reluctance on the right-hand side, right? Reluctance on the right-hand side. So technically, these are all in series together, will be in series together. But for this problem, I'm going to calculate them separately because you need to involve the mean path on each side. So if you're looking at, needless to say that this whole thing will give you a certain phi, and this phi would be the same. This is like the current in an electric circuit. As long as the elements are in series, then all of these flux values should be the same for all of these elements, right? So in order to find out the reluctance in each of these sides, we need to come up with the mean path. So this L up means the mean length of the upper leg. So as you can see, in order to calculate the length, we come up with the whole B and then half of A and half of C. So this would be the average length associated with the upper leg. Is that correct? Is there any questions? So this is the upper part. Same thing for the lower part. So that would be equal to the upper part because the dimensions are same. For the left part, you have to do half of D plus half of E plus half of F plus E. And for the right part would be the same because the dimensions are. So in terms of the length, average length, the two sides and the upper part and lower part would be the same. So these are calculations of the paths. And then we have to come up with the cross-section. So the cross-section through which the flux is passing through for each of these paths would be different. So for the left part, it would be this A times G, right? A times G. So that A and that G, these two will make that cross-section for this path on the left-hand side. So A in the upper part would be D times G. So D times G would be the cross-section for the upper part. For the lower part would be F times G. For the left-hand side would be A times G. For the right-hand side would be C times G. Now that we came up with the L's and A's, then we can come up with the calculations of their reluctance. So the reluctance would be L over mu times A, and mu would be mu R times mu zero inside the magnetic materials, right? So this, since I put all of my units in SI, then my calculations would all come up with the SI units. But I needed basically my outputs in certain units. So make sure that you display them in this certain form. So the reluctances need to be shown by kiloamp terms over Weber. So they are calculated in SI, but we need to display them in kilo. So therefore, for displaying purposes, this is the command. This is the command that you can use in MATLAB. This puts everything in series, converts basically whatever you got in here, multiplies that by 1e minus 3, or divides that by 1,000 to make it in kiloamp terms per Weber. And finally converts that number, whatever number you have in here, converts that into a string. So this is the first string that attaches to the second string and gets attached to the third. So if I go ahead and run the code, you will see that you receive basically the outputs in this form. All right, so this is from the reluctances. In the second part, we want to find the value of the current that will produce a certain phi. And for that, we know that F in this magnetic circuit, F for the magnetomotive force should be R total, which is the combination of all the R's, times phi, right? And F is equal to Ni, the number of turns. So that would be R total times phi. So from here, you can find out your I as R total times phi over N. So this is how this has been done. So this is the total R. This is here. This is phi here. And this is N. So I would be found at amps, and we require I to also should be shown in amps. So this is how we display that. The second part. Now it's talking about the flux density. So although the flux would be the same throughout this whole whole path, because all of the reluctances are in series, but the flux densities would be different because of cross-sectional areas. So flux density for each section, the upper section, lower section, left and right sections would be based off of the phi value over the respected area. So here we find the E's in Tesla, and then we show them also in Tesla. The second problem is showing a core with 3 legs with the dimensions that have been mentioned in here. We have n turns on the leftmost. Depth is D. Depth of the core is D. And the relative permeability is mu R. It is constant. We want to know what flux will be existing in each of these 3 legs of the core. So the phi in this area should be the same, the flux. And here, the flux should be the same. And on the right-hand side, also the flux should be the same. So we can basically draw the magnetic circuit to make that more clear. And also, we want to find out the flux density in each of these paths. So let's go back. This would be our magnetic circuit. So we have like a DCF. And then this is one reluctance on the left-hand side. Then you would have one reluctance on the middle side and one reluctance on the right-hand side. Also here, this middle side would be really 2 reluctances. One is associated with these 2 magnetic segments, and one would be associated with the gap. So this is going to be your magnetic circuit. So this will result in a phi on the left-hand side, which needs to be divided into 2 paths. This would be the phi in the middle part. And this would be the phi on the right-hand side. So R left would be found from the average length of the magnetic core here, from here to here. R and reluctance in the middle would be the sum of basically the reluctances in these 2 paths. We need to find the average lengths here. The R of the gap needs to come from this air gap. And you know what these air gaps are. These air gaps are where your basically motion happens in your motors and generators, right? We need to have these air gaps because you put the rotor of the generator, for example, that air gap so that it can rotate and move. And finally, this whole path would be considered the reluctance on the right hand. So we find the total basically magnetomotive force. R on the left-hand side, here we have 2 times A over 2 plus B plus C over 2, right? Here, the average path is A over 2 plus B plus C over 2. Make it 2 times to count for the lower part. So that's that part. And then on this left-hand side would be like A over 2 plus A over 2, so 2 times A over 2 plus B. So that counts for this left-hand side here. So A, or the cross-section on the left-hand side, would be A times D. A times D is the core depth. So reluctance on the left-hand side would be L over mu times A, right? R on the right-hand side would have exactly the same dimensions, the same characteristics as the left-hand side, because this is a symmetrical shape. So R on the right-hand side would be the same as R on the left-hand side. Now let's go to the middle part. The middle part, we have 2 times A over 2, the total path length, plus B. There is a tiny part of the air gap, which is not part of the magnetic core. Really putting this G, whether you put it or not, will not make much difference in your final calculations, but I want it to be more accurate, so I put that here. This is the cross-section in the middle part, C times D, and reluctance would be L over the total mu times A. Now, we haven't calculated the air gap's reluctance. Remember, for the air gap reluctance, we should also increase 5% the cross-sectional area, the effective cross-sectional area, to count for fringing effects. What does that mean? So when you have an air gap, and you have a flux here, so the magnetic basically field, most of it will go through this air gap, but since basically this is basically the whole air, some of the magnetic basically field will try to go from the around it area. So in order to account for that, we should increase basically the effective cross-sectional area by, for example, 5% to make the reluctance smaller. So that's what this means in here. So for that purpose, you for calculating the reluctance of the air gap, you put the air gap length over. Remember, do not put the mu r here, because here we are in the open air, right? So if you make that mistake, you will get a wrong number. If you multiply mu0 by mu r, you will get a wrong, basically, reluctance for the air gap. All right, so let's go back to our magnetic circuit. Here, if you want to find out phi, then it's as if you put your R on the left-hand side, plus you have to have your R middle plus your R gap, and put it in parallel with R on the right-hand side, right? This becomes your R total. So that we used in here, R total is found. And then from there, you can find phi, which would be the phi in here. And then that phi will get spread into 2 parts. So you would use the reciprocal rule. So because this is the phi is working like a current, right? So the current will flow in the other paths based on the reciprocal of their impedances. So in other words, R phi in the middle part should be phi on the left-hand side times R on the right over R on the right plus R in the plus these 2 values. So that's what's been done. And then the rest of that would go to the middle. So that's what I did in here. Phi in the middle, we found it, and phi on the right-hand side, we could use the same rule, but I mean, an easier basically calculation would be just subtract basically these 2 values. And same thing for the B's. So the B's would be different based off of the cross-section in their respective parts. So we put B left, B middle, and B right based off of their phi values over respective cross-sectional areas. So we have a ferromagnetic core with a relative permeability of mu r, which is constant. The dimensions are given, A, B, for the most part, in G1 and G2. The depth of the core is given as C. The air gaps are given. Because of the fringing effects, the effective area of the air gaps is 5% larger than their physical size. If there are n number of turns in the coil wrapped around the center leg, and the current of the core is known, what is the flux in each of the left, center, and right sides? And what is the flux density in each of
in the air gaps G1 and G2. Right. So if you want to do this problem, we can basically look at it from this perspective. There would be the magnetic circuit would be as if you have a source magnetomotive force in the middle, and then there would be a reluctance here in the middle. The whole left-hand side, this side plus this side, that would be basically one reluctance that are coming in series, and then it gets in series with the reluctance associated with G1, right? On the right-hand side, you can add up these two reluctances again together, and the reluctance associated with this G2, they come in series ultimately, and in the middle you have its own reluctance. So it would be something like this. You have two reluctances on the left, two reluctances on the right, and one reluctance in the middle. So based on the problem, these have been called, we didn't call anything, so we can just call them whatever we want now. So I can call it R left, R right, then R G1, R G2, R M, meaning the middle, and this becomes the total phi. Phi on the right, phi on the left, phi on the middle. So this is phi in the middle. These will be divided into phi on the right and phi on the left. Phi on the left and phi on the right. This is right. The other one is left. This is right. This one is left. Okay. So in order to find out R on the left side, we have to consider the average length on the left side, which is half of A plus B plus half of A plus another half of A plus B plus another half of A. So A, so it would be something like A over 2, A over 2, A over 2, B, another A over 2, right? And another A over 2, another B, another A over 2. So it's as if you have 3 times A plus B. Right? So L on the left would be 3 times A plus B. And you can basically subtract this portion, minus G1, to be more accurate, minus G1, although it won't affect basically the results very much. We do that. L on the right-hand side would be just because of the symmetry, would be the same, 3 times A plus B minus G2. And in the middle, we have A plus B, right? A plus B. So L in the middle would be just A plus B. So the reluctance on the left-hand side would be a left over mu0 times mu r times A, which is the cross-sectional area, which would be how much? It would be, how much is the cross-sectional area for the left-hand side? C times A, right? C times On the right side, that would be similar. Mu 0 mu r times CA. In the middle part, mu 0 mu r, that would be again CA. And also we need to C times A. C times. And for the gaps, our G1 is just G1 over. Do not make the mistake to multiply, basically put mu r here. This is air gap, right? So mu 0 just times C times A and times 1.05 because of the fringing effect. Same thing for G2. That's G2 over mu 0, C times A times 1.05. So once you get all of these reluctances, then it would be easy to find out the phi in the middle. So our total would be R left plus RG1 in parallel with R right plus RG2 in series with this whole thing in series with R of the middle. And then you would find phi in the middle as MMF, which is n times I, right? Over our total. That's phi in the middle. Once you find phi in the middle, then phi on the left-hand side would be equal to phi in the middle times. So the phi's would be divided based on the reciprocal of the two reluctances. So we should have R on the right over R on the right plus R on the left. Phi on the right would be just phi in the middle minus phi on the left. Correct? Once you find the phi's, then the b's would be just phi's over the areas, which we have the areas are all the same. So b on the left would be phi on the left divided by a, which is equal to c times a. The same thing for the right and middle portion. Going over a two-leg core like this, the winding on the left leg is N1, on the right side is N2. Coils are in the directions shown in the figure. The dimensions are shown. What would be the flux produced by the currents I1 and I2 in respective directions, assuming a relative permeability of mu r. Okay. So this is really the start of the transformer section or transformer chapter of the book of our course. So we're really getting into the point where you see that the direction of these currents becomes important. So, all right. So let's look at it in here. You have a current in here, right? The current would be in a way that it will create a field in this way. Isn't that so? The current is the thumb, and the four fingers are basically curling in a way that they wrap around the wire, and then through the core, they try to go up. So for this one, goes this way, or this one goes this way. So it's as if they are trying to follow each other. So they're adding to each other. For this one, look at here. This is the left side is similar to what you had in the previous problem. So it's going up. For the right side, it's again this way, right? So they just oppose each other. They try to cancel each other, in other words. Here, if you take basically the direction this way, that would be N1 I1 plus N2 I2. Flux leakage means that when you have a magnetic core, if your magnetic core is ideal, meaning that if mu is equal to infinite, this means ideal magnetic core. Then if there is basically a source of magnetic flux, like let's have a source here which provides current, it gives you basically an H, and then H creates a B, and then flux, right? So all the flux, H and B vectors, everything would go entirely inside this. The flux would go entirely inside the core. So there would be nothing in the air, nothing, none. This is because we have an ideal magnetic core in which mu is infinite. But in reality, we don't have ideal conditions, so your mu would be a few thousands, but not infinite. This means that out of the H that we get into this magnetic material, there would be some flux that is in the air around us, and that's called the flux leakage. The leakage of the flux, because magnetic materials basically permeability is not infinite, we would get some leakage in the air. This is what we mean by leakage. However, when we're talking about fringing, we're talking about this air gap that exists that is meant to basically contain parts of the electric machine, the rotating parts and so on. When we have basically out of basically whatever has been, we're not talking about those magnetic flux that has been leaked. We're talking about the magnetic flux that is existing inside this core. When it reaches the air gap, it not only basically goes through this path, but also a little bit through around that direct path. This is called the fringing effect, which practically, as you can see, it's as if the cross-sectional area has been increased a little bit by 5%, which is impact is to reduce the reluctance, not to increase the reluctance, because reluctance is L over mu times mu 0 times A for the air gap. It's when A increases, it's as if the reluctance decreases. Okay, so this is the difference between the fringing